Hey guys, welcome back to this channel. Today's video is one I've been wanting to make for a while. We're breaking down CVE 2026-2964, a prototype pollution vulnerability in a JavaScript audio library that under the right conditions can lead to a full remote code execution on a Node.js server. We're going to cover everything: what the CVE is, where it was published, the background theory you need to understand it, a full lab walkthrough where we actually trigger the exploit and then we patch it live. By the end of this video, if you are a beginner, you will understand what prototype pollution actually means. If you're advanced, you will have a working lab and a complex attack chain to add to your toolkit. So let's not waste time and let's get into it. So the first thing I wanted to show you is where the CVE lives. I'm on the SentinelOne vulnerability database right now, and if you search for the CVE 2026-2964, this is what you get. The affected library is called Web Audio Recorder.js. It is an open source library built by the developer Yuji Mian, known as Higuma in GitHub. Its job is to record audio in the browser and encode it into WAV, OGG, and MP3 format. Pretty innocent stuff. The vulnerability was classified as a prototype pollution issue. We'll get into exactly what this means in a moment. The severity is rated as low, but as we're going to demonstrate today, under the right conditions, this leads to an RCE, which is anything but not low. This is another vulnerability database, VulDB, I like to cross-reference. It gives us additional context and often different technical details than what you get from NVD or SentinelOne. Good habit as a researcher is to always look at multiple sources, never rely on just one. The interesting thing about the CV is what the researcher noted in their write-up. Most implementations use hard-coded configs only vulnerable if a developer builds a config object from user input. Example, letting users customize audio settings via Forms API without validation, unlikely but technically possible. So this is a conditional vulnerability, and that's an important concept for any pentester. Not every vulnerability in a library means every app using that library is exploitable. Your job is to find whether the vulnerable code path is actually reachable. We'll come back to this again during our practicals. Alright, now that we know what we're dealing with, let's understand the core concept behind this vulnerability before we touch any code. Let's build this up from the ground. Even if you're an experienced pen tester, stick with me here. Understanding this deeply will make the attack chain make total sense. In JavaScript, almost everything is an object. Think of an object as a box with labels on it. Simple. Your box has two labels, name and age. You can read them anytime. Now here is where it gets interesting. Every single object in JavaScript has a hidden label called proto. You don't create it. JavaScript adds it automatically, and this label doesn't store your data. It points to a parent object. Now, why does this parent relationship exist? Because of a rule called prototype inheritance. The rule is if JavaScript looks for a label in your box and doesn't find it, it automatically goes up to the parent box and looks there. And if it is not there either, it goes to the grandparent and so on until it hits null. Now, the final ancestor that every single object in JavaScript ultimately inherits from, that's called object.prototype. It's the grandparent of everything. Every object, every array, every function, they all eventually trace back to object.prototype. Let me give you an analogy that will make this stick. Imagine a school. Every student has their own lunchbox, but there is one central kitchen that all students share. The rule is if a student is missing something in their lunchbox, they automatically get it from the central kitchen. Object.prototype is the central kitchen, and every object in your JavaScript program is a student. Now ask yourself this: what happens if an attacker poisons the central kitchen? Every student's food is affected automatically. Even students who packed their own lunch perfectly, they never touched the kitchen, but the kitchen's content flow down to everyone. That is prototype pollution. The attacker doesn't touch your object, they poison object.prototype, and every single object in the entire application gets affected. Now for accessing this object.prototype, just go to any website and in the console, just type this. And here you can see you can access the object.prototype. And for detecting the prototype pollution attack, you can refer the Portsfigur's website. They have well-documented articles, vulnerable labs, so you can practice it there. I'll leave the links below in the description. Now, one more concept before we hit the code. This one is specific to why our exploit needs two proto hops instead of one. Once again, if you don't understand this payload, I'd recommend you to go through the Portsfigure Labs once, or you can just search any prototype pollution video on YouTube and just go through it once, so that the basics are all sorted. So now, imagine three generations of family. Grandma is the object prototype. She owns the central family house everyone inherits from her. Then comes mom, the web audio recorder prototype. She has her own room in the house. And then you, the web audio recorder instance. You live in your mom's house. The rule in this family is the same. If you don't have something, ask mom. If mom doesn't have it, ask grandma. Everyone in an application shares the same grandma, that is the object.prototype. So if you poison the object.prototype, then all the objects in that application gets affected. In our exploit, if we send just one proto in the payload, we land in mom's room. That is, we only pollute the web audio recorder objects. Nobody else cares about it. But with two underscore proto hops, we jump from mom straight to grandma. And grandma is shared by literally every object in the entire Node.js process. That's the global pollution we need. So, with the theoretical architecture of the vulnerability, let's start building the lab now. We're in our project directory and let's initialize an npm project here. I'll open VS Code in it. Now let's create the file index.js. We need to import some library first. Now, for this project, we need to import the library web audio recorder.js. This is a critical point as we can't install it with npm. I don't know why, but the specific version that we require is not there in npm. So we'll have to download it directly from GitHub. So for this, in our package.json, we can define a script to automatically download it whenever we run the project. Now, if we open the repo inside this lib directory, here we have this web audio recorder.js file. Click on raw and copy this link. Then in the script section, remove this code and add this. So here, when the script gets executed, this will first create a directory called lib, and then it will download this file and it will output it into lib web audio recorder.js file. And after it's done, it will echo this message. So this means the file you are running in this lab is the exact same code that a developer would have included in their web application. Nothing is rewritten or hard-coded, just the authentic CVE recreation. Okay, now let's go to the index.js and write a condition like if the file is not being loaded, then we'll generate this error. Now we'll set up a minimal window stub, then execute the library file in our global scope. Our first part was to load the library. Now, if we go to the web audio recorder's code, then in the last line, you can see this. So after execution of this library, we pull it off our stub, and now we have the real constructor here. So we also need to add window here. Otherwise, it will throw an error. Now, why are we using this function to load this library? So instead of using require, we read the file as a string and execute it in Node's global scope using Node's built-in VM module. This lets the library attach itself to our global window object, exactly how it would behave in a real browser. So now the library's code runs and then it executes this, and now we have access to it. Here with this code, we were able to create a fake browser, and we also need a fake audio recorder or a fake source node because this library is expecting it. Otherwise, how a user will record, right? So let's create that. So the web audio recorder constructor expects a real browser audio context source node. That is a live microphone input. In our Node.js lab, there is no browser, no microphone. If we pass nothing, the constructor would crash even before reaching the vulnerable extend call, which is mentioned here. If you click on this URL in the VulDB, then this is the actual vulnerable code. So this function expects a live microphone input. So think of fake node as a crash dummy. Its only purpose is to keep the constructor alive long enough to reach the vulnerable code. Each arrow function does nothing, it just stops a crash. We don't care about audio recording, we just care about the extend call. So here is a detailed diagram of how the fake node is interacting with the web audio recorder constructor. So you can just pause it and see it once. So now we have a fake browser environment and also we have a fake audio input. So now if we go back to the vulnerability write-up again, here we can see that the author has mentioned that it is only vulnerable if a developer builds the config object from user input, that is letting users customize the audio settings via forms API without validation. So now we'll have to build this form and allow our users to customize these audio settings. So let's see how we can do that. Here we'll have to create a post request. And let's say we'll create an endpoint. So here this endpoint will receive a post request and the body will contain the configuration provided by the user, and the application takes this configuration directly from the request body and passes it into the web audio recorder constructor. No validation, no sanitization. This is exactly what the CVE researcher warned about. User input reaching the constructor configurations configs parameter. And inside the extend function, the for in loop iterates over every key in the source object, including proto. There is no check anywhere that says skip this key if it is dangerous. It just blindly copies everything. When the key is proto and the value is an object, the extend function recurses into it. And that recursion is what allows the attacker to work down the prototype chain and reach object.prototype, that is the grandma. Now let's write some additional check to verify that the payload we are passing is actually getting set. Here is the check that will confirm if we are able to pollute the object.prototype, and this is the RCE gadget. Now I want to be transparent with you here. This specific gadget is the one I wrote myself for the demo. No real app has exactly this code. But here is the important point. In production applications, gadgets like this exist naturally. For the ones who doesn't know what a gadget is, it is simply a piece of code that already exists in the app that does something dangerous, but only activates when a certain condition is met. After pollution, properties that were previously undefined suddenly have values, and that can trigger logic that was never meant to run. The specific gadget changes per application. Your job as a pen tester is to find pollution first, then hunt for gadgets in the application's dependency tree. So now finally let's just create the listener. Now first we need to install these libraries. Now just run the command npm run setup. Now here you can see it has downloaded a library. Now let's run node index.js. Our website is now ready. So here we can see our application is up. Now let's create a call request to hit the config endpoint. Here I'll create a separate file to create our payload. Now here we'll have to define our payload, that is the configuration object. Now if we check the VulDB article, then there we have this payload. So I'll just copy it. And we need to add one more thing here. We need to pass this payload into the config object, that is this, as it will be fetched from the request body. So I'll have to add config at the start. Now let's test the payload. Okay, it says couldn't be resolved to post. Probably here we need to do it capital X. And here we're getting an error. Okay, okay, it says received audio config undefined. Go back to our index file. Okay, here we're getting the audio config as undefined. That is, it's printing this value. So probably there is some issue with our payload. Let's go back. Okay, here also we'll have to change it to a backslash. Now let's copy it again. Go back here. Now we're getting a different error. But here you can see we were able to pollute the object, but now it's giving a different error. So let's fix that. Okay, here we don't actually need the variable. We can just remove it. Save it and let's rerun it. I'll just restart the server. The pollution is successful, but the worker is not defined. So here we need to also ensure that the worker is available in both browser style window scope and in the global scope of Node as well. So for this, I'll just have to add this. Now save it. And another thing here also, we need to make sure that the colon is not there and it's here. And also here you can see we've imported this library. So all right, now let's rerun the application and check. So here you can see we're getting a successful message. And here also you can see we have polluted this value. So let's walk through this payload, like exactly what is happening. Here, first, the attacker crafts a JSON payload. Then comes the body parser library, which deserializes this JSON payload and extracts the request.body.config, that is the config value, that is this payload. Then this is passed directly into the web audio recorder constructor, and no sanitization is being done. Then the extend function recurses through the proto label that we're injecting into the code, and it makes the two hops and it pollutes the object.prototype directly. And then comes the final RCE gadget. So we'll see that now. Okay, first of all, here we want to need brackets here, as it is not a method, it's just a string. So we'll just keep it as it is. And we'll also have to download this library. Here we'll do npmi. And now here you can see in the comments we've written that it only executes if the toString gets polluted on object.prototype. That is, we need to pollute this toString variable into the string pond. So for this, we need to modify the payload. Just copy the value. Here, instead of this polluted variable, we'll have to write toString, and instead of success, we'll have to write pond. Now copy this payload again and rerun the server. Just inject the payload. And here you can see we're successfully able to execute the command and get the RCE. We have executed the command whoami on the system, and it has returned the value accordingly. And here also you can see RCE is exploited successfully. So if we come back to this diagram again, when we've set this value to pond, then every object in the Node.js process now has toString is equals to pond. Then the gadget condition fires, the toString value becomes pond, and there it is. The server ran whoami and returned the result. We went from a JSON payload in a HTTP request to a code execution on the server, all because the library's extended function didn't check for the proto label. Now let's talk about the fix, and I want to show you two layers of defenses. So let's see. So here, first we'll sanitize the keys before they reach the constructor. So here, this is the app level fix. Before parsing any user config to the web audio recorder constructor, I strip out dangerous keys. Even if the library's extended function is vulnerable, the payload never reaches it with the dangerous keys intact. Now, we'll make a list that only allows the known expected config keys. Here, we'll only accept keys that the app actually needs. Everything else is silently dropped. That is the recommended approach in production. Here you can see we've allowed the encoding methods only for this, and after that, these are the only configurations that is required. So we will only pass this and nothing else. And now we'll implement these functions inside this post request. And now we'll implement the second function, which checks the allowed list. And similarly, we'll also pass this safe config in here. And now let's check again if we're still able to insert our payload. Just pause it and restart. And here you can see our status is success, but we weren't able to pollute the values. You can see the pollution check is also false, and we're getting the value as undefined. And it has blocked this dangerous key. And after the sanitization, this configuration object becomes empty because in every step of it, we've inserted the proto payload. And then this empty config object is being passed onto this constructor. So this was the path before the fix, and this is the path after the fix. Previously, we were taking raw user input and then no sanitization of that input was being done, and we were directly passing it into the constructor. And then it was further polluting the extended function, which leads to the execution of the gadget, and we were able to get our RCE. And in the fixed path, we were taking the raw user input and then we're sanitizing it first, and then we're checking if the provided configurations are present in our allowed list, and then after checking everything we are passing it onto the constructor, and hence it is ensuring that the object.prototype is clean and the attack gets blocked. So this is the breakdown of the CVE 2026-2964. This is the final flowchart of how the payload into the vulnerable code, so you can check it. Here is what I want you to take away from today. Prototype pollution is not just a theoretical vulnerability. The path from a JSON payload to RCE is real, and we just walk through it live. Second is not every CV in a library means every app using that library is exploitable. Always trace the code path. Always ask this question, does user input actually reach the vulnerable function? Then third, the double proto label is not a magic. It's just the prototype chain. You need two hops because this inside a constructor is an instance, not a plain object. Fourth is defense needs depth. Sanitize keys and use an allow list. One layer can be bypassed, two layers are much harder. And then the last one is when you find pollution in a real engagement, don't stop there, hunt for gadgets. The pollution itself is a proof of concept. The gadget is what turns it into an impact. Alright then, let's wrap this up now. The lab code, all the payloads, and the fixed version are linked in the description. Clone it, run it, break it, fix it. That's how you actually learn this stuff. If this video helped you, hit the like button. It genuinely helps the channel grow. Subscribe if you're new. I drop content like this regularly. And if you have any questions, drop them in the comments. I read everything. And also, please do share this video with your friends, with your colleagues, anyone who might learn something from this video and can use it into their pentest engagements or through their bug hunting process. So that's all for this one. I'll see you in the next one. Stay curious and stay ethical. Thank you.